Jeff. This is Joe.
Hey Joe, how are you doing?
I am doing well. Oh, I'm doing well. I always forget to look at the camera instead of the screen. So, well, I'm sorry you couldn't make it, but I'm very happy that you could give this talk. So thank you very much.
Oh, well, I'm delighted to be able to do it, and I really regret that I can't be there in person, but it just wasn't possible.
Yeah,
Uh,
okay, I understand. It's a long way too.
yeah, yeah. But I'm glad that this fest is occurring and it's well deserved. So I'm delighted to be part of it.
Okay, thanks. Good. Okay, I'm going to give the microphone back to Rusty.
Uh, all right. We continue to the next talk by Jeff Harvey, who will talk about mass renormalization for strings. Please.
Okay, thank you very much. So you can all hear me, I gather.
Yes.
So I'd like to thank the organizers for inviting me, and congratulations to Joe on an incredibly successful career, and I'm sure many discoveries to come. So Joe was, I believe, my second graduate student. Um, Now looking back and realizing that obviously I'm older than Joe, but not a lot older, I kind of wonder if I actually knew what I was doing at that point in my career. But anyway, things worked out well. Joe and I think our first paper was a paper on open strings on orbifolds. Orbifold compactifications of string theory had just been formulated, and it seemed interesting to generalize our knowledge of closed string theory to open strings. And it was not an entirely successful paper. We found some interesting things, but didn't really come up with a completely coherent story. But in our defense, I think I would say that probably a completely coherent story would have required discovering D-branes, which unfortunately we didn't manage to do. But the next paper that Joe wrote was a paper that he wrote by himself. I think we had some discussions that started it. Basically, the question was, all right, now that we have string theory, it's a finite theory. How do you understand things like the beta function for gauge theory by doing one loop computations in string theory? And Joe wrote a very nice paper and did essentially all of the work. And this paper, I think, definitely had a significant influence on further developments. And in fact, what I'm going to be talking about today is some work that could have been done a few years after this paper by Joe's, but was not done. It was just sort of a problem that I think was overlooked. And I hope it's an example that there's still some old school string computations that are interesting to look at and that remain to be done. So what I'm going to talk about is based on a paper that came out recently, a few months ago, with my graduate student, Taiwei Hu. And it really combines two results that emerged in the late 1980s. So it's very old school. The first development is the analysis of what are called Faye-Iliopoulos terms. When you have a U1 gauge theory in a supersymmetric theory, there are certain terms that you can add to the Lagrangian called Faye-Iliopoulos terms. And more recently, it's been understood that there are some issues involving some issues with anomalies when you couple to supergravity. But the terms that we're going to be discussing, it also involve couplings to the dilitons, so they're not strictly FI terms, they're FI-like terms. And it was realized that these terms are induced at one loop in string compactifications that have a U1 gauge factor where the fermion content is anomalous. And I'll explain that, of course, the whole string theory is not anomalous. So this was first discussed by Dine, Seiberg, and Witten, and they didn't do explicit string computations, but argued for the effect. And then Addick, Dixon, and Sen, and Dine, Ichinose, and Seiberg, and others followed up on this with explicit computations. So one of the results of their computations was that there were scalars that were massless at tree level in these compactifications, but that acquired a mass at one loop order. So the second development that goes back to the late 1980s is the observation that if you take heterotic string theory on a circle, now this could be starting in 10 dimensions and compactifying down to 9 dimensions on a circle, or it could be, as I'll discuss here, a Calabi-Yau compactification down to 4 dimensions, and then an additional circle to go down to 3 dimensions. But in any case, when there's a circle factor like that, there is an infinite tower of perturbative BPS states. And I'll explain the structure of these for those of you who haven't seen this before. And so the result of the paper that I wrote with Taiwei is that a very similar calculation to the one that was done for the scalar mass corrections leads to a one-loop correction to the masses of these BPS states. And this is quite interesting because it's kind of in contradiction to standard non-renormalization theorems that occur in superstring theory. So here's an outline, and I will try to stick to the allotted time. I'll explain what the compactifications are that we're going to study and why they're kind of an interesting test of our ability to do string perturbation theory. I'll remind you about perturbative BPS states on a Calabi-Yau times a circle. I'll very briefly sketch some aspects of the one-loop string computation without getting into the gory details. I'll say what our main result is, and then I'll discuss open problems and implications of this. And I think there's actually a lot to do that would be interesting to follow up on. Okay, so we're going to be considering SO32 heterotic string rather than E8 times E8 on a Calabi-Yau manifold X, and we're going to be using the standard embedding of the spin connection in the gauge group. So what this means is that we have a Calabi-Yau manifold X. It has holonomy SU3, and we decompose SO32 into SO26 times SO6, and then SO6 has an SU3 times U1 subgroup. And we turn on a gauge field A in SU3, which is equal to the spin connection omega on X. That gives rise to a 2, 2 sigma model on X. And such sigma models have been, studied to death in the string theory literature. This results in a theory that has SO26 times U1 gauge symmetry, and the massless spectrum consists of the standard supergravity multiplet, a dilaton axion multiplet, the moduli of X, SO26 times U1 gauge supermultiplets, and then some charged matter. Now, a standard index theory computation shows that the charged matter comes in, depends on the Betti numbers of X, and there are H11 scalars or matter multiplets in the 26, the vector of SO26 with U1 charge 1, and a singlet of SO26 with charge -2. And then there are H21 guys with the opposite charge, that is 26 with charge -1 and singlets with charge 2. And you'll notice that the trace of the U1 generator, which I'll call Q, over the left-handed fermions is 24 times the difference between H11 and H21, which means it's 12 times the Euler number of X. And since X generically has a non-zero Euler number, that means that there are anomalies if you just look at the massless fermion content. The fact that the trace of the U1 is non-zero means that there's a U1 gravitational anomaly. If you work out the rest of the anomalies, there's a U1 cubed anomaly, and there's also a U1 SO26 anomaly. So this is what I'm calling a pseudo-anomalous theory. It looks like there's an anomaly when you look at the massless fermion content. But of course, we know that in compactifications of consistent string theories, you don't get anomalies. And the way that works is that there's a version of the 10D Green-Schwarz mechanism which works in 4 dimensions. Under gauge transformations of the gauge field, there's a shift of the axion field. There are couplings of the axion to trace R wedge R and trace F wedge F, which vary under gauge transformations in such a way as to cancel the fermion anomalies. And then the fact that the axion and the gauge field transform the way they do means that the axion kinetic term has to be modified with the coupling to the gauge field, which shows you that the theory wants to have a kind of Higgs-like mechanism where the U1 gauge field eats the axion to become massive. Now, the one-loop string computation that I mentioned before leads to a modification of the Kähler potential with a constant that's proportional to the trace of this U1 generator. So it's proportional to the gravitational anomaly. And this modification to the Kähler potential, once you chase it through, leads to a potential for the charged scalars, phi I. So the potential that you get is 1 over g string squared times this quantity squared. And if you expand it out, we can count orders in g string. There's a quartic coupling of the phi's, which is tree level. There's a one loop term, which is quadratic in the phi's and proportional to c. So that's a one loop mass correction. And then there's a two loop term, which it would be a cosmological constant in the vacuum where the phi i's are zero. And when there's a cosmological constant, that leads to a dilaton tadpole. And all these terms have been computed in string theory to verify that it has this form. Now, this is an interesting test of our ability to do string computations because this is the only example I think that's known in the literature where supersymmetry is broken in the vacuum with the phi i's equal to zero. Clearly, you're not at the minimum of this vacuum, but it's believed that it's restored in the vacuum that is at the minimum of V, where the phi's have a non-zero expectation value. And since the phi's are charged, they also contribute to breaking the U1. And so you've got to, what happens is that the U1 gauge field eats a linear combination of the phase of the phi I that condenses and the axion. And the structure of this theory has been analyzed at the low energy effective field theory. But it's an interesting test because you have to kind of shift things, mix things at different orders in perturbation theory in order to study this. And it's believed that supersymmetry is restored, but I don't think there's actually a proof to all orders in string theory that this works out. There's a very nice paper by Ashok Sen using string field theory to study this. And also a nice paper by Ed Witten who uses, well, which I'll mention later. Okay, so we want to compute something different, corrections to BPS masses. So let me remind you of what the BPS states are. So once we're on a circle, the momenta on the left and right moving part of the string differ by a winding term proportional to L. L is the winding on the circle, M is the momentum. And that means when you look at the mass squared formula for general perturbative string states, as usual, there's a level matching where there's a contribution on the left, which depends on the momentum on the circle and the number of left moving excitations and left. And then on the right, there's a contribution from the right moving momentum on the circle and then the right moving excitations. The BPS states are in the ground state on the right, on the superstring side of the heterotic string, which means n right is a half and then a Schwartz sector or zero in the Ramon sector. And for those states which have arbitrary left moving excitation but are in the right moving ground state, the mass formula is simply m squared is K3 squared, which is a charge, as we expect for BPS states. And then there's a relationship between the number of left moving excitations and the product of the momentum and the winding number on the circle. What this means is that there's in effect an infinite open strings worth in terms of the degeneracy of BPS states that have momentum and winding on the circle. And you can either think of these as BPS states, point-like states in 3 dimensions, or if we took the radius of the circle to be very large, going to infinity, we could think of these as cosmic string configurations in 4 dimensions that are BPS and made from fundamental strings. So standard string perturbation theory allows us to compute the mass shift of general states at one loop by computing the two-point function of the vertex operators that create those states. Those correspond to inserting those states at 2 points Z1 and Z2 on a torus, and then integrating over the positions and integrating over the modulus tau of the torus. And the vertex operator is a product of left and right, and I've written down the corresponding vertex operators here. On the right, this is the vertex operator, I think, in the Noah-Schwarz sector. And then on the left, we can have arbitrary n left, and we chose a particular form of the left-moving vertex operator that allowed us to do explicit computations in an orbifold limit of the Calabi-Yau X, because we wanted to be able to do everything explicitly. But in fact, many details of such a computation can be seen for a generic X without necessarily using the orbifold limit. So just to give you the high points of the calculation, the integrand is naively zero for a reason that usually leads to non-renormalization of the mass shift of massless states or BPS states. Namely, when you contract the fermions in this correlation function, you naively get a factor of k squared, where k squared is zero for massless states. For BPS states, it's not zero, rather it's the formula that relates the mass squared to the momentum on the S1. But if you work slightly off shell with k squared not equal to zero, you find that when you integrate over the separation between the two vertex operators, so z is now the difference between them. You can set one z to zero by translation invariance and integrate over the other one. There's a factor of 1 over z to the 2 plus 2k squared. And that, when integrated over z, gives rise to a 1 over k squared, which cancels the k squared and leads to a finite contribution. So this cancellation and working slightly off shell is exactly what was done in the old computations of the shift of massless states. And it works the same way for BPS states. If it makes you uncomfortable to work off shell in string perturbation theory, where we know it's not completely kosher, there's an approach via super Riemann surfaces that was developed by Ed Witten, which allows the computation to be done on shell. And we showed that formalism could also be used here. So this is not absolutely necessary. It's just kind of to explain what's going on. You're then left with having to compute the expectation value of a kind of vertex operator for an auxiliary D field. And that can be computed just sort of by hand using canonical techniques. And it turns out to be proportional to the trace over the left-handed fermions of the U1 charge. That is the anomaly. So this computation has a few changes from the mass shift of massless states, but it's structurally very similar because the right moving part of the vertex operator for BPS states is the same as it is for massless states. So our main result is that for perturbative BPS states of this form, or BPS strings, if you think of these as cosmic strings in 4 dimensions, with U1 charge Q, there's a one-loop mass correction. The correction is 12Q times G string squared. And this is the correction in the unshifted vacuum. We haven't tried to put in an expectation value for phi. So I think this is kind of interesting. We know other examples where there's a one-loop correction to the BPS formula. For example, that occurs in Seiberg-Witten theory. So here are some implications of this computation and a few open problems. There are BPS states with arbitrarily large Q, so this mass correction can get quite large, even at small g string. Is there some need to reorder string perturbation theory in these situations in order to get reliable results? We're working in the unshifted vacuum, and we believe that the true supersymmetric vacuum has a non-zero expectation value for some of the charged scalar fields. Those can also contribute to shifts to the mass of BPS states through cubic couplings, phi I to BPS states. And to determine the true BPS mass spectrum, we would have to compute these couplings as well and the work in the shifted vacuum. That seems like a complicated computation, although it might be doable in string field theory, but probably not doable by me since I've never actually done a computation using string field theory. We have not understood this phenomenon from a space-time point of view. Recall that in Seiberg-Witten theory, I mean, the formula relating the mass to the central charge is fundamental and is true to all orders. But what happens is that there's a renormalization of the central charge, which leads to a normalization of the mass. But here, relating the mass to a central charge is quite subtle because in 3 dimensions, if you think about, well, either a point mass in 3 dimensions or a string in 4 dimensions leads to a conical deficit angle. That deficit angle in infinity makes it hard to define the supercharge. In fact, it's even more subtle than that. The subtlety was pointed out by Witten, and there was a follow-up paper by Becker, and Strominger, and they showed in a toy model that the supercharge you need to derive the BPS formula survives due to a cancellation, but the supercharge that pairs bosons and fermions does not exist in these kinds of spacetimes. So anyway, this should be understood better. There are old field theory arguments that FI terms are not renormalized past one loop order. I don't think anybody has established the same thing here in string perturbation theory. It'd be interesting to know whether that field theory argument generalizes. And we also don't know whether there are non-perturbative corrections here coming from, well, you could describe them as wrapped branes or field theory instantons. That hasn't really been studied. And then finally, there are other string and M theory compactifications that are discussed in the literature, which also lead to pseudo-anomalous U1 factors. And it would be interesting to see whether our analysis generalizes to these cases and whether BPS states also get normalizations to their mass there. I would guess that they do, but the details of the analysis might look a little bit different. So these compactifications that have these pseudo-anomalous U1 factors continue to be a really interesting test bed for the techniques of superstring perturbation theory and string field theory. And I'm not mentioning, because I haven't really studied the literature, but I think these are also of quite a reasonable amount of interest in the string phenomenology community because they have particularly interesting features. Axion physics has interesting possibilities. The cosmic string configurations include not only the kind of axion strings that we think of as related to superstrings, but also kind of local gauge strings. And there's a lot of interesting structure in these theories. So I think they deserve more attention from the string theory community. So I think I've stayed within the time. So I'd like to thank you again for listening, for the ability to give this presentation. And I'd like to offer my congratulations to Joe on a very successful career. I can't really take any credit for his success, but I was very happy that I was his advisor and that I was there to see him begin his career and his adventures into particle and string theory. So thank you very much, and I'm open to any questions you might have.
You have mentioned in your introduction that in the original heterotic calculation of the Dick terms, there was expected a two-loop contribution. As far as I remember, nobody has done this calculation. Do you know anybody who has done it?
I thought there was a follow-up paper. I'm trying to remember now. I know there was a follow-up paper by Michael Dine and I think a student of his that computed mass corrections to fermion terms. I can't remember off the top of my head. I somehow was under the impression that somebody had done the two-loop computation, but perhaps not. Maybe there's just an indirect argument that it should be there and nobody's actually done it. I think it would be interesting to study the issue of higher loop perturbation theory in these theories, string perturbation theory. If you send me an email and I can remember the paper, I will send you a note, but it could be that I'm misremembering and nobody has done it.
Thank you, Jeff. So Ashok did compute mass shifts using string field theory. So in your case, could you apply what he did to your calculation, or is that clear, or is it more complicated? Or
I think that's possible. I mean, as I said, sort of my problem is I've never actually done a calculation.
yeah,
in
no,
string
I
theory.
avoid it like the plague. So
I don't think I probably would not be the person to do it, but I don't see any obstacle to it. We know explicitly what the vertex operators are, so these BPS states could certainly be included in a formulation of string field theory, and his techniques could be used. So I think that would be one way of trying to organize the computation of the BPS spectrum in the shifted vacuum, at least including all the one-loop effects. I don't know to what degree it's possible to study the question to higher loop order. I think it's quite interesting, either in string field theory or in maybe using Witten's super-Riemann surface formalism to see whether there's a non-renormalization theorem at higher orders. Again, that's what happens in Seiberg-Witten theory. There's a one-loop correction to the mass of BPS states. There are no higher order corrections in perturbation theory, but then there's an infinite tower of non-perturbative corrections. So it would be interesting to know whether this is similar at the level of perturbation theory in that there's a one-loop contribution, but no higher order corrections in string perturbation theory. But I don't think that that's known at this point.
thank you.
Yeah, thanks for the beautiful talk, Jeff. This is an attempt to comment on the question what has been done at two-loop string perturbation theory. The closest to this that I could find is a Do-Fong paper from 2013, archive number starting with 1307, which is about the two-loop vacuum energy for Calabi-Yau orbifold models, commenting on heterotic string calculations with differences between E8 cross E8 and spin 32 model. But okay, this is a vacuum energy. Your talk was about two-point functions, so I certainly understand that a bit more technology is needed to go from the vacuum energy there to the two-point functions of interest.
But they compute the two-loop vacuum energy with the pseudo-anomalous U1 factor. Is that right?
Okay, I just have the abstract in front of me. Not sure. Maybe I'll look at it later and email you.
Okay, well, that would be great. Thank you very much.
Thanks to you.
If there are no further questions, let's thank Jeff again.